am ready.
Awesome. Leticia as well, thanks so much for having me. Yeah, this is more like homecoming, like chatting with folks at Gemini is always fun. Uh, so uh, I am Sid Sade. I'm a doctoral student in epidemiology at Columbia University, and we have been sort of like doing some of the things that I thought could be useful to chat about at Gemini, given that I also have been involved in some of the healthcare access and global search rework that's going on. And so today I thought one of the things that I could talk about was uh, looking at looking at how we think about exchangeability, spatial confounding, and how in certain methods we can now leverage spatial confounding as a way of getting better treatment effects. Um, a lot of kind of like the verbiage or language that I will be using today is more like epi like driven. So if that feels uh kind of like out of place, please let me know, and I can like clarify things as we go along. Right. Right. I would like to thank Adam and Nav, who were sort of like my study buddies for so let me maybe give a little bit of context. So we worked on this method in one of our courses at Columbia, which is EPI 6, which is basically uh, advanced epidemiological methods. Uh, this course was like taught by Dr. Matt Lamb, who works at the he works at like the Global Health Center that like Columbia has. Um, and then Adam and Nav were sort of like my study partners for for like working on all of this. So definitely thanks to them. And what I'm presenting today is um, more of like an adapted version of what we have been working on for a while now. I would also like to thank Chris Morrison, who is my lab director at Geospatial and Applied Sciences Lab at Columbia. Cool. So we'll talk a little bit about what spatial epi, issues of for causation in spatial epi, confounding, and then I'll introduce the method that we have been kind of like trying to learn, understand, and use. It's called distance adjusted propensity score matching, or uh, DAPS-M. And then we'll also quickly go through a working example of DAPS-M that we did. Um, all of this is like all of what I'm about to present is also written up as a report, and we also have sort of like R code to do things. So if anyone's interested, I'm happy to share those with like anyone. Um, I can also try and figure out a way to put them online, but I will need to sort of like check with like my co-authors before doing that. So, but yeah, I'm happy to like share it one-on-one with people. Cool. So, till until recently, although like spatial epidemiology has been a growing field, there was no real consensus on what it is and what it does. Um, Chris wrote like a scoping review sort of thing uh, last year to bring together a whole bunch of literature and people to put together a definition that would be helpful. So at least right now, we think that spatial epi is application of theory and methods from epi, geography, and statistics to describe spatial distribution of health outcomes and to analyze associations with possible causes to inform intervention and improve health. And so yeah, like I feel like within spatial epidemiology, we sort of sit at the interface of geography, and a lot of like biostats. Uh, but the goal, or sort of like the horizon in vision is always how we can influence better health outcomes. Although we talk a lot about just like, although, yeah, we talk a lot about like just spatial stuff, in terms of dealing with data, we always have data that's like spatial and temporal. Uh, and so the idea is to look at spatiotemporal data to better identify causes of disease, but to also understand what are the effects of either individual or population level interventions. Uh, that, especially the second part, which is intervention effects varying in space and time, that's where I think we have unique challenges compared to a lot of other, uh, not just epidemiology, but also a lot of other spaces in public health and medicine. So, um, causality in spatial epi, we are still moving more and more towards the potential outcomes framework. Uh, and so again, a lot of this is like epidemiology driven. If this does not make sense, please let me know. But the idea is that uh, you can you can sort of think about your intervention or your exposure in the context of a hypothetical experiment. And in that hypothetical experiment, you would have potential outcomes for different treatments. And so the framework is then based around when you can identify these potential outcomes using the data that you do have. And so sort of like the central problem of like all of like causality, again, not just in epi, but like everywhere, is that ideally we would like to get at individualized causal effect. So what would be the effect of a treatment when I got the treatment versus had I not received the treatment. And so, but depending on whether I get the treatment or not in reality, you can only see one outcome for me and not both. And so that's sort of, yeah, the fundamental problem of causality. Potential outcomes framework tries to get away with that by using certain assumptions. So exchangeability is the assumption that you have two groups or two individuals that are comparable to each other for everything else except your treatment. Positivity is the assumption that in all the strata of like your other like variables, your confounders, you have data. And so the comparison that you're making is supported by data and is valid. And then consistency is the assumption that you, well, a sort of like you have like a well-defined intervention, and then your units of analysis, so like individuals or like groups or uh yeah, in case of spatial epi, like census tracts or whatever, are not influencing each other's outcomes. And so yeah, POF uses these assumptions, but it also sort of brings the inference to the level of some like group. So we are always looking at like average effects instead of any individual effects. Um, Especially within when we talk about like spatial data, it's that assumption of consistency that gets broken because we know that uh, places that are closer to each other may be correlated versus like their outcomes may be correlated versus places that are away from each other might be more dissimilar. Uh, and so that kind of like breaks the consistency assumption at the very start in a lot of cases. Um, we'll talk more about exchangeability as we go along in this presentation. So in all that to say that the validity of these assumptions, uh, in case of like social, spatial treatments or exposures, is difficult to assess. Uh, Specifically today, we will focus on just exchangeability and not so much on positivity or consistency. Even within exchangeability, I'll talk more about spatial confounding and what that means and how it looks like, how we can use it. Does that make sense? Should I keep going? Also, I cannot see the chat box, so if at any point there are like questions, I will need help
Cool.
to like
I'll let
navigate.
you
Yeah.
know, Sid, if
Yeah.
the questions come by, but I think it's okay. You can go ahead.
Okay. Awesome. Thanks. Okay, so super quickly, we can look at like the challenges that we face as either like theoretical or spatial or statistical. That's not to say that that's like the nature of like the challenges, but how we try to understand or reconcile them. Um, we can have like edge effects, meaning that there can be factors outside the spatial unit that can influence the intervention effects or treatment effects of our spatial unit. We can have construct validity issues, so basically figuring out uh, whether the exposure that we are looking at, whether that's really suitable to be assessed at like any given level, right? So uh, yeah, when we talk about things like neighborhood crime, uh, what variable do we really use that can proxy the construct of neighborhood crime, right? So that's always challenging. And then we have modifiable aerial unit problem, which is yeah, which also like goes back to all the literature that we usually talk about, even at Gemini, about like ecological fallacy and stuff. And so here the idea is that as you change like the unit of like spatial unit of like analysis, it your findings may change. And so there's always a reason to choose certain like scale versus like not choose it. We can also have like kind of like connected to them, we have like statistical issues. Uh, The first one is spatial autocorrelation, which I think, yeah, I just referred to in the like before like two slides. So yeah, things that are closer might be correlated to each other versus ones that are far away. Uh, Again, this sort of like violates the uh, independence assumption that a lot of standard statistical models, including linear regression, use. And so, yeah, like kind of like taking care of that becomes important. We can also have a problem of endogeneity. So this is when you, so endogeneity is when your error is not independent across units. Again, in spatial data, due to at times due to spatial autocorrelation, but also maybe due to other like unmeasured confounding, you can have endogeneity problems. We can also have spatial interference, which I referred to when I talked about consistency assumption. So the idea that exposure of one unit may be impacting the outcome of the neighboring unit. Uh, and so that sort of like violates the yeah, the consistency assumption, which is also called SUTWA, which is stable unit treatment value assumption. Um, and then finally, we have spatial confounding. So you can have unmeasured spatial variables that can influence both your exposure and outcome. I should have said at the start that I'm sort of using exposure and treatment uh yeah, like interchangeably here, although yeah, like there are people who get like finicky about that kind of stuff. But yeah, um again, today we'll be focusing more and more on just the spatial confounding problem uh of all of this. Okay, so whenever we have observational, so like non-RCT data, we know that we may have problem of non-exchangeability, meaning that we know that our control group and our treatment group may not be exchangeable with each other. If they are not exchangeable, we need to start thinking about how to make them exchangeable, either by design methods, so like by designing our study in a way that they are more comparable, or once we are done with the data collection at the analysis level. And so in the context of like I guess like in the context of like spatial confounding, um, we can think about like sources of like non-exchangeability as either like unmeasured and measured. And so measured confounding is basically all the other like covariate data that we collect apart from the treatment and outcomes. So for specifically with spatial data, what we can do is now think about a part of unmeasured confounding. So like part like a piece from like that brown part uh, adds spatial confounding. So these are unmeasured spatial variables that may be linked to your exposure and outcome. However, there is some use for them, as we'll see in the methods going ahead. So uh, yeah, like the only sort of like takeaway from this that I want you all to have is that within the unmeasured confounding, you can think of
Okay.
like slicing that up
Jadi bwana yule mdogo bwana
to
sija mdogo miaka mitatu.
consider that some of that unmeasured confounding is happening due to spatial attributes. All right, and so distance adjusted propensity scores can be a good solution for dealing with the problem of unmeasured confounding. Uh, what we are doing here is that we are adjusting using the standard propensity scores, and I I don't remember if uh Joao, if like have we had like a data talk on like propensity scores anytime recently?
No, not recently. I think we covered something, I want to say like July last year, where we talked
Yeah.
about merging data sets, but we didn't get too much into it. So if you want to give a high level review, it would be good.
Yes. Okay. Cool. Yeah, because I remember seeing it, yeah, seeing something in like the yeah in like the calendar, but I don't know when it was. Okay. So yeah, I'll get into like a really short intro of like propensity scores, but we use standard propensity scores and match our treatment groups based on the similarity between their propensity scores. But we also use geographic distance uh, to sort of like inform these balancing scores. So that's the first like part of like what like yeah what we are doing here. The idea is to control for unmeasured spatial confounding using this. And so the within the score itself, the balance that we are trying to achieve uh, is it's like the score value itself, which I'll come to in a bit, but which is based on your measured covariates and the spatial proximity measured using some metric of like distance. Wait, wait. Okay, cool. So, a super quick overview of what propensity scores are. Propensity scores are is well by definition, I guess it's like probability of like treatment conditional on measured covariates. So when we use, and the idea is that this can then like this probability can then be used as a way to make your treatment and control groups exchangeable. Uh, the assumption that we are making is that once you measure the treatment on all the other covariates, you sort of like remove that connection between the other covariates and the outcome, and you like front load all of it into what was the probability of getting the treatment, and then you can just yeah, then you're like free to look at the relationship between the treatment and the outcome. So that's one. The central assumption to doing all of this is also that you're you, you're basically saying that I am measuring all of my confounding using the covariates that I have. So beyond these, I have no unmeasured confounding. Um, and as we saw, like in observational data, you're always going to have some unmeasured confounding. So uh, this is sort of like taking a bite at this blue part that we talked about, but you still have a lot of like, yeah, unmeasured stuff that this cannot deal with, right? Um, However, what you can do once you have like propensity scores is you can do a whole bunch of things with like propensity scores. I'll only focus on what's like relevant today, which is like matching, right? And so what you can do is based on propensity scores, you can match uh, people in the treatment group with like those that are untreated. Uh, and matching kind of like gives you what we call average treatment effect among the treated. So you are conditioning on the fact that you know who got the treatment, and then you're looking at among them what's the size of like your effect. Okay, but yeah, as we said, we do have unmeasured confounding, and so that's why even when we use like propensity scores and try to improve our like exchangeability or comparability, we know that we do not have like full exchangeability there. However, in spatial like data settings, yeah, using like spatial confounding, we think that we may have a solution to sort of like dig a little deeper and deal with not all of that unmeasured confounding, but at least some of it. Um, so here is the central thought of like all of what we are doing, right? We have variables that we did not measure, but we know that those variables are expected to have some variation, which is spatial in nature, right? And so again, like all of this is following from like our initial like laws in like geography or like demography that say that things that are close to each other are more related than things that are like farther apart, right? And so what we can do is we can leverage this spatial structure of correlation, uh, measure it using some metric, whatever we want, right? Like spatial autocorrelation, like we have measures for those, like Moran's or like a whole bunch of like distances, right? Uh, and so we can leverage that spatial structure and say that this metric now acts as a proxy of at least a chunk of my unmeasured confounding, right? So basically, what our method is dealing with is using this sort of like, yeah, I mean, I'm not that great at like colors, but I want to say this is like orange. But yeah, it's sort of like using this orange part to now say that this blue and orange part is what we are kind of like adjusting for. And so we have reduced our unmeasured confounding compared to like this, right? So
Mhm.
we still may have unmeasured confounding, but we are trying to like take a stab at the problem like one step at a time.
Yeah, so you said so you assume that the spatial confounding is gonna resolve a portion of that unmeasured confounding?
Yeah,
And
so
is this portion like a random portion, or can you tell how much it would explain, or I don't know.
yeah, so I mean there's like no real way of saying, well, I guess there's some way of saying like how much unmeasured confounding you like can have. But yeah, like we don't know what like each, yeah, like there is no way of saying how much like each like the slice of like this pie is. But what we are trying to get at is that maybe our measured confounders can take care of some. And then maybe with this distance adjustment, we can take care of like the other part. And so that's how we are trying to like minimize the unmeasured confounding part. But that's a good question. Can we say like, yeah, what each size is? I don't think we can like definitively ever say that in like observational data. Um, but I do know that there are like sensitivity methods that try to get at that question. So like once you are done with the analysis, there's something called an e-value that you can
Hmm.
calculate to say like, yeah, like after I use like all the covariates, how much unmeasured confounding would be needed to like completely nullify like the
Yeah.
effect that I saw. So yeah, there are like, yeah, there are like kind of like post hoc like hand wavy thing, like yeah, ways to like get at that. But yeah, I don't think there's like a bottom up answer to say, yeah, like how much like yeah, each of these pie pieces would be. Yeah, I mean that's just like the problem of like dealing with like observational data in general. So I guess yeah. Uh, but yeah, that's a great question. I mean I know that that's a question that a lot of people yeah, that like bugs a lot of people anyway. So cool. All right, so we'll keep going, I guess. Yeah, so that's what like the method that yeah, I guess we have been like trying to learn and use in like our group has been kind of like looks at. So it looks at a way to go beyond the traditional propensity score matching and use a distance measure to sort of like improve the match. Uh, this was initially introduced by Georgia and kind of like her like group at like Harvard, and I think now she has moved to like Florida. I also think that this was like her like part of like her PhD like thesis. So uh, yeah, yeah. Also a quick note. So this works really, or well, yeah. I'll take a step back. But like this kind of like is useful for spatial data sets where you have yeah, like where you have like units uh and like kind of well-defined like treatments for those, right? So let's say we are looking at like hospitals and a bunch of hospitals received uh an intervention, yeah, maybe received like a new protocol of how to take care of like maybe snake bite patients. Uh, and then there's like a bunch of hospitals that did not receive that protocol, right? So this is a good method to have a study comparing the two groups. But then instead of just using like hospital characteristics, you also use spatial characteristics to make sense of whether you can get away what yeah, like how much like unmeasured confounding can you do away with and make the hospitals like more like comparable or exchangeable. So in general, like any like point like processes that we have, this works really well with that. And so that's the other reason why I thought this would be like good to talk about at like Gemini, because I know we do a lot of like healthcare access and like injury data, and like all of injury data is like point data. Like it's not like cardiovascular like research where yeah, you have like disease among like patients for like years and years without knowing whether they actually have the disease or not, right? So this works really well with like short time interval acute outcomes, and where you know that your exposure are like well defined in like space. Cool. Okay. um The next half of like what I'll talk about is sort of like designed more as a tutorial. And so I'll try to go through that uh, as quickly as possible. But if there are questions, like let me know. It should be fairly simple though, if the if the idea of like what we are doing and why we are doing it is like clear. So just to recap, we are combining spatial proximity and standard propensity scores so that we can control for both measured confounding and at least some part of the unmeasured confounding. That's the goal. And so distance adjusted propensity scores are like literally a sum of those two things. So you have some weighted difference of the propensity scores between like two units. So let's say like unit I and unit J. Uh, and then you have the distance between those two units. And we'll sort of like break down this like equation as we go along. So there are like two parts to that. Uh, I don't know why my brackets like moved that way. They were supposed to be more aligned. Anyway, but yeah, there's a standard propensity score component that you see on the left, and then there's a distance component that you see on the right. The weight that you saw there can like, it can have a value from like 0 to 1. And so a lot of what we are doing in terms of analysis is uh, kind of like figuring out that weight value. So you can either do it manually, which means that, let's say, which kind of like goes back to like Joel's question. So let's say you have a good idea as to uh like for whatever reason, whether you are like an expert or you know something from like the theory or like past literature, but let's say you have a good idea of like what, like how much of like unmeasured confounding is like can be like spatial. So if you think that you have a good idea of that, you can choose the weight manually, or you can have certain like data driven mechanisms to do it for you. Essentially, when we choose the weight as 1, we are only matching on like propensity scores. When we choose the weight 0, we are only matching on distance. Uh, and so in practice, what we would like to do is choose like the smallest value of W that's kind of like optimal for both like the covariate balance while also looking at like spatial like proximity. Within the distance, there are like, again, like there are like so many different ways of what, like in terms of like spatial uh like spatial work, what like distance would be. The simplest would be like the typical like Euclidean distance, and so you can like restrict the matching within like the specific distance, or even like if you have like larger geographic units, you can like sort of like restrict it to like only match with like hospitals within the state and like not go beyond the state boundary. So you can like do all of those things. But you can also try more complicated like distance measures if those seem suitable to you. And again, like we'll go through like some of this ahead. Uh, and finally, in even in like a regular or like traditional like propensity score match, you have something called like caliper, which is basically what, so like let's say I have a propensity score that like ranges from like 0 to 1. Uh, and when I'm like matching people across like control and like treatment groups, like how similar do their propensity scores have to be for me to consider them a match, right? Whether like, do I think they have to be like exactly equal, or let's say someone has a propensity score of like 0.4, someone has propensity score of like 0.5. Is that like close enough for me to like match them, right? And so that's the caliper distance. And so like there, like again, there are like a whole bunch of like considerations around the caliper distance that you would need here as well. All of that to say that our goal is to have the standard PS with the distance-based propensity matching, with the distance-based like proximity matching, and achieve like better exchangeability when we think that there is unmeasured spatial confounding. What this matching technique allows us to do is that we can get our average treatment effect among the treated that even other like sort of like propensity score matching techniques give us. Okay, so we'll go through like the four major considerations that you need to think about when you are doing this with your data set. The first one is selecting calipers. So caliper is number of sort of like so it's measured in terms of like standard deviations of your propensity score. So it's a number of distance adjusted propensity score standard deviations beyond which you think that your propensity score is like too large to produce an appropriate match. And so there are like since you have like two components to like your score, you can do it like in different ways, right? So you can either have a caliper uh, threshold like defined for the entire score, or you can have calipers specifically for the propensity score, and then you can have a caliper separately for the distance adjustment. So what this means is that you can either say that my distance adjusted propensity score ranges from like 0 to 1, and I'm going to say that anything that's within like 0.1 is similar. If like two people are, or like two like units are outside of that difference, they won't be used for matching, right? Or you can say that let me first match people on like let me first have a caliper for propensity scores of like 0.1, and then let me have a separate caliper for distance adjustment and say that people who are outside of like 200 miles or like whatever will not be matched to each other, right? Uh, there is some simulation stuff to show that choosing either one would not make a lot of difference. Uh, it would be easier though to use like a caliper directly for like taps and not do like separate calipers. The second thing is what distance measures that you use. Like I said, the easiest one is like our typical Euclidean distance. And so this is basically just like the standardized distance uh, that you use. Um, However, you can, I mean, again, like the like distance at an abstract level is just the idea of figuring out in relative terms how close or far apart things are. And so let's say if you're looking at really long distances, maybe Euclidean distance is not great because like, well, Earth is sphere, and we know that those distances are calculated differently. But you can also look at travel time. So for instance, if your research question is about uh, access to healthcare or like those sort of things, instead of using like actual like geographic distance and like uh yeah, like kilometers or like miles, it might be more useful to talk about like travel time. You would still do the standardization the same way, and you would still like call it a distance measure, but you're now looking at time. Uh, yeah, and it works like perfectly well. Like it shouldn't like make a difference. But yeah, it's mostly your research question that would determine what distance measure you want to look at. With respect to selecting matches, there are like a whole bunch of like algorithms that you can use to select matches. I don't want to like go into too much, yeah, like too many details of that. Uh, well, partly because even like I don't know like too many details about it, but yeah, like matching and sort of like algorithms to like do matching are like a standard like statistical problem. Um, what yeah, like the takeaway I think that I would give is that you sort of have like greedy algorithms that basically do like uh yeah, that go in like a step-by-step way about matching like one pair at a time. And you can also have like optimal like matching algorithms uh typically with like increasing like sample size, you want to go for optimal match instead of like greedy match. Uh, the yeah, kind of just like a really simple explanation of how like optimal matching works is that once it is able to like find a match, it sort of like removes that pair, uh, and then then it just looks at like everything else that's like available without like having to go through like the whole like data set in like iterations. Um, the idea is that we sort of like match our treated and like control units. And again, this can either be full like one-on-one match, or you can have like one to many matches, or like yeah, any other way. But the idea is that you sort of like match units in a way that they are now comparable for the entire like distance adjusted like propensity score. Okay, and then the last consideration, and which is probably the most important one here, is how do we select the weights that are used in the score? It can either be domain knowledge based, or you can use data-driven methods. So again, like when we talk about the weight, uh, I kind of want you to think about it as you have like the distance adjustment part, and you have the standard propensity score part. And what the weight is trying to do is say which one I think is more informative for making my control and treatment groups comparable, right? And so that's like sort of like the trade-off or balance that you're trying to find. Um, in terms of like the data-driven ways to find optimal match, what you do is you look at the absolute standardized difference of means uh, to uh, based on like all the measured covariates. Uh, you give like a certain threshold of what like that difference should look like, and then you're trying to find the value of weight, which would just get you like right at that like minimum or like that tolerable uh like standardized difference, which again is like yeah, which I think you like kind of like implicitly without knowing, we sort of like do that in a lot of different places, including when we are looking at like the healthcare like access algorithms and figuring out, yeah, looking at all those like network like algorithms that try to figure out which hospital is the closest and sort of like those sort of questions. Okay, so the weight is governing the balance between propensity score based covariate adjustment and distance based unmeasured spatial confounding adjustment. And so the plot here is from the original paper that described DAPSM. And so what you can see is that you can set like a threshold for your, so the Y value here is like the uh, ASTM, so like the standardized, uh, yeah, like the absolute standardized like difference of means, and the X value is the weight value. And so and each like the line here represents a covariate. The original paper looked at like power plants and like sulfur or like some like environmental exposure at like power plants and how that results in changes in like health outcomes among like people living near like the power plants. And so what this is trying to tell you is as you go from like as you increase the value of the weight for each covariate, you will see that their absolute like standardized difference of means will change. And so you want to choose a value of weight where that difference is like lower than your threshold. So like a weight of like 0 here probably does not work for like most covariates. So uh, which means that your treated and untreated units are not balanced on that covariate. But as you go along, you will see that you sort of like start achieving that balance. And somewhere maybe around like zero point 0.5 or like zero point 0.3, you have that balance for like most covariates. So that's sort of like the weight that you probably want to like choose, right? Okay. And again, we'll come back to this. So this is probably a little bit more complicated, but we'll do like a toy example of this quickly ahead. So in terms of like so what this would look like. So if you have like a weight of 0, which means that you are only matching on distance, yeah, you'll see that basically you get a match of like all the places, all like the power plants that are like close by, right? If you do naive like pair matching, which is basically just matching on like standard propensity scores, yeah, they kind of like get matched like anywhere within the US. And these matches are based on how similar the two power plants looked based on their other like measured, like observed covariates. But when you do matching based on the distance adjusted propensity scores and sort of like you use that optimal weight of like 0.5, you see that it's almost like you have like pruned the knife matching and sort of like found like a midway between like these two, right? Uh, okay. Super quickly, a working example of this. So we recently had a paper where we looked at an intervention called leading pedestrian intervals in New York City. And not in this paper, but in like aftermath of this, we sort of like applied the DAPSM to our problem. So I'll quickly go over what's the problem and how we did it. Uh, Leading pedestrian intervals are basically intervals at intersections that give pedestrians kind of like a head start of like a couple, like 7 to like 11 seconds in New York, so that they can start crossing the intersection before the turning vehicles can like turn. And so that's our intervention. It's really, so if you think about it, the reason DAPS-M is useful here is we have like precise intervention. So like we know where like which intersections within the city have these intervals, right? And then the outcome that we are looking at were, and so yeah, this sort of like the map of New York and like how those, yeah, treated and like untreated like intersections look like. Uh, and then the outcome that we are looking at is, um, oops, my bad. Oh, anyway, uh, yeah, the outcome that we are looking at like are motor, like the crash outcomes between motor vehicle and pedestrians at intersections. So again, we have a really well like spatially defined out like acute injury outcome uh, that yeah that we know where and when it happened. The covariates that we measured to create balance here, and so we just took like a cross section of like our larger data from 2017, and we looked at like the number of like intersection legs. So that's basically if you have like 4 legs, that's like a, if you have like, yeah, 4 legs, that's like a cross section. Um, my bad. If you have 2 legs, that's like a cross section. Uh, if you have 3, that's like a T. And if you have 1, that's basically just a straight road. Uh, we also looked at the perimeter of the intersection, so kind of like the circumference of like how big an intersection is, because there's like variation of like how large those are in like New York. Some are like really small and others are much larger. And we also looked at sort of like the distance between two intersections with the idea that if you have like, yeah, like the longer the roadway between the intersections, there's like a larger probability that people will speed in between them. And so that's like a good like proxy for like speeding. And then we looked at pedestrians killed in the previous year as like a covariate, because we also know that the Department of like Transportation installs these leading pedestrian intervals depending on whether there was a fatality in previous years or not. So again, instead of like going into the details of this particular question, what I want you to focus on is that we have an acute injury outcome, we have well-defined spatial exposure or like treatment, and then we have like 4 covariates that we could measure. And so this is kind of like the reality of like observational data, right? Like we would like to measure a lot more covariates. We don't have that. We just have four that we think work the best here. Uh, and so using the four covariates, we build our propensity scores, and we kind of like see how the overlap between the treated and untreated group looks like. And there is like a decent overlap, at least in parts. But you can also see that the propensity score values range from 0.25 to like 0.50, maybe a little above that, which means that we do not have units that are perfectly matched only using the standard propensity score. And so this is sort of like the hint that you have a lot of like unmeasured confounding. Can I put a number on like how much? No. But do I know that there is like significant unmeasured confounding? Yes, because my even like the best propensity score is like not going above like 0.5. The higher limit here is like 1. So like if the measured confounders are like enough to match are like enough to like accommodate like all the confounding, I would have a propensity score of like 1, but that's not happening using the four covariates that I'm using here. And so, yeah, now now I want to like sort of like bite away at that unmeasured confounding piece. And so I'm going to start looking at distance as a way to do that. Uh, oh, this is just like a screenshot of like the code. But again, I'm like happy to like share the code if people want to like use it. But yeah, it's like doing the analysis for this is like really, really simple. Uh, but I think that's why it's also important that you understand what you are doing, because yeah, like otherwise it can get like like weird and incorrect really quickly. But yeah, you just have like one chunk of code. So this is my piece of code where I'm trying to find a weight using the greedy algorithm. My bad, not the weight. Yeah. Well, part of finding the weight is like doing the matching. So yeah, I'm trying to do that using the greedy algorithm. As we discussed earlier, I'm defining a caliper for the entire score. I'm giving it like a list of weights to like choose from. So it's going to go from like 0 to 1 in steps of 40 to find what's like the optimal weight for my data set. I'll plot the balance of the weight across like the covariate like ASTM scores. I'm giving it like a tolerance cutoff of like 15% for like how high can the ASTM go. And then finally, based on like my optimal weight that I get from here, I'll just run the matching, like the final like matching to get my like effect size of how effective were the leading pedestrian intervals in reducing the pedestrian motor vehicle crash outcomes at intersections. So here it's much cleaner. This is similar to sort of like the covariate weight plot that we saw earlier, but since we just have four, it's much simpler. So when we are looking at full data, there's like a covariate on which we do not have a good balance. But as we go along, we start to improve that balance. And it's somewhere like maybe here that we have like the best balance for like all of them. Okay. So we sort of like, I mean, again, this was just like exploratory analysis. So we looked at if we do just like if we just do like distance matching, we use like 1900 like pairs of like intersections, and we get like an average treatment effect among the treated of like 0.23. So that's 23 fewer injuries for like 1,000 intersection years. If we take like a weight of 1, so that's like just entirely PS matched, we increase our like sample size, yeah, because like we are just using covariates for the matching now, and we get like an ATT of like 0.15. And when we use the optimal like weight matching, our optimal weight in this case was about 0.8. we reduce our sample size because we are trying to sort of, yeah, like use everything that we have for the match. So that's also like another consideration that you should have, whether how much like power you lose when you do these sorts of matches. But then we also reduce our effect size in terms of what we think is the real effect. And I will say that like the effect that we found for, yeah, in our like main and like larger analysis was actually 6 like injuries per, yeah, like whatever, like intersection year. So yeah, this is like probably quite close to that. Okay. You can also look at how your estimate of like that effect is changing across the weight values. And this is like a good way to see whether your optimal like weight algorithm is like working or not. Like if you see a lot of like variation in these, yeah, it's probably not the best idea to like choose one specific weight. Rather, you should like, yeah, look at the effect estimate across like weights. Cool. So we are trying to use unmeasured spatial confounding to improve conditional exchangeability. This is only effective if we think that there is like, yeah, like spatial confounding. If you don't think that's the case, yeah, you're just like screwing up your like original like match. So yeah, don't do that. Uh, this is useful for like ecological studies, which is a lot of like what we do at Gemini as well, especially at least a lot of what I do in like global surgery at Gemini. So yeah, uh, at least right now, I don't think there is like a DAPS-M method that can look at like longitudinal data. I will say that there are like other methods that can like do that. But yeah, like so this is like this works best if you have like single time point data. Uh, and then yeah, like this just deals with like confounding. It cannot deal with like issues of like selection bias. It cannot deal with like spatial interference. Again, there are methods that deal with spatial interference as well. Uh, yeah, that was, yeah, that's it. And yeah, I have a document that has like these like, I mean, beyond these references, that kind of like gives like a good like reading list and like tutorials, the code. So if anyone's interested, I'm happy to share those. But it would be really cool to see if, yeah, if someone at Gemini wants to like use this for a problem that they have been dealing with, where like, yeah, like the last thing that I'll say is that if you have like observational data, treatment group, some control group, and if you have like spatial data on them, like hospitals, this is like really good to make them more comparable. Uh, yeah.
I mean, that's awesome, Sid. Like as you were going with your presentation, I mean, first, thank you for this. This is really cool, and really cool seeing how you applied this to this problem. But as you were going, I kept thinking about the work we're doing in the Brazilian Amazon, especially with the ecological analysis. Like, for instance, we want to see the impact of heat waves on hospitalization in the rates for different ICD codes. The level that we got was to, well, we can map where those heat waves are. We're using satellite information. We can cross-check the heat waves to where the hospitals are, and then we can measure, hospitalizations the day before, the after, or something like that. But as you were saying, if we could apply this to a similar to this setting, we could eventually get to a more sensible, I mean, more, I want to say like even like a sensitivity analysis of matching the hospitals versus that are really similar or they are close enough to actually measure the impact of this treatment, which is the heat wave or something. So I really think that this could be a direct application to that. Yeah. The the question that I had, as you were saying that the limitation of not being able to do this as a longitudinal data, would you say that maybe doing something like, let's say you have 10 years of data, you do the analysis with the current data, and then you do the analysis with the data coming from 10 years ago. Do you think that that's an alternative to at least compare like the progress of an intervention, the progress of this effect over time?
Yeah, definitely. Yes. So I think, and even like in the original paper, I think what they did was that the like the exposure was like, let's say in year one, and the outcome was from year five. And so the
Mm,
reason that they could say that they are looking at a causal effect is because it still like establishes the temporality, right? So I
hmm
think you can always do that. Uh, you can, in fact, I would think that as sensitivity analysis, you can also do that. You select heat waves in a given year and then look at its effect for like every like 2 or like 3 years. And
hmm
so the idea would be that that effect kind of like reduces over time, right? If there have been like no more heat waves, right? So uh yeah, no, that's yeah, you can do that. Also, wave is a really good exposure because we know that there is going to be like spatial confounding for sure. So yeah, in general, yeah, like environmental exposures would work quite well. Yeah.
Cool. Cool. Oh, that's great. Let me think about that a little bit, and I'll go back to the references that you have there on the recording, and maybe I'll reach out to you with some more questions, and see if we can get that going.
Yeah. And yeah, I mean like whatever you need, like I'm happy to like yeah, chat more. Uh I'm also like out of like my like classes now, so it's just like teaching and research. So I definitely have like more like time to like do stuff. So yeah.
Cool. Cool.
Got
Well,
it.
we are a bit out of time. I'm sure that Sid will be more than happy to respond to questions via email or Teams as well. I'm not sure if you are still in the Gemini Teams, right? So you
I
probably
am.
will
Yeah,
still
yeah.
get message. So, but anyway, thank you so much for coming, and thank you all for being here today.
Of course. Thanks. Bye-bye.